Welcome back to my channel. In this video, we will be talking about the tricellular model. The tricellular model was developed based on the premise of differential heating of the Earth's surface. It provides a simplified explanation of how atmospheric circulation patterns give rise to distinct weather and climatic conditions at various latitudes. Atmospheric pressure is the weather element which refers to the weight of the atmosphere pressing down on the Earth's surface. Atmospheric pressure can be described as being either high or low. The average atmospheric pressure at sea level is 1013 millibars. Whenever air rises, the weight of the atmosphere is lifted, resulting in atmospheric pressure being low or getting lower. However, when air sinks, the weight pressing down on the Earth's surface increases, so pressure gets higher. Air rising depends on three main factors: convection, convergence at the surface, or relief barrier. Convection is where air rises because of being heated. When the air is heated, it gets lighter, and because it's lighter, it will float. Convergence involves air flowing into a particular point. When this occurs at the surface, the air is forced to rise. Relief barriers, such as hills or mountains, also forces air to rise. When winds blow across a mountain because it cannot go through the mountain and it cannot go back, it is forced to rise. Now, similarly, air sinks when it is cold and therefore heavy. It also sinks when convergence occur in the upper atmosphere. And the third way that air sinks is when it is moving along the leeward side of a mountain. The leeward side of a mountain is the opposite side to the windward side. So, whereas the air rises on the windward side, it descends on the leeward side. Atmospheric pressure is symbolized on a weather map by lines similar to contour lines known as isobars. Notice on the map that where the values of the isobars are low, pressure is low, and where the values are high, pressure is high. The difference in pressure between two places is known as the pressure gradient. Pressure gradient is the initial force which causes winds. Winds blow from areas of high pressure to areas of low pressure. Pressure gradient may be described as either being steep or gentle. So, on a weather map, steep pressure gradient is shown by closely spaced isobars. Steep pressure gradient causes strong winds. On the other hand, gentle pressure gradient results in light winds and is shown by widely spaced isobars. So if we observe the map, notice that we have high pressure at Blue Valley and low pressure at Stand Terrace, which means a pressure gradient exists. Air will therefore blow from Blue Valley to Stand Terrace. Notice also that the isobars are far apart at Blue Valley and closer together at Stand Terrace. So it means that the winds will start off light as they move from Blue Valley and then will get stronger closer to Stand Terrace. After winds are initiated by the pressure gradient force, they can be modified by other forces. So, for example, as the wind blows, it may be influenced by friction, and friction generally slows down the wind. Another force which influences the wind is the Coriolis force. This is the apparent deflection of the winds to the right in the northern hemisphere and to the left in the southern hemisphere, sorry. And this force is as a result of the Earth's rotation. It, however, doesn't normally affect uh, winds blowing over short distances, so it mainly affects large scale winds. Since the sun's insolation varies with latitude, places near the equator will receive more heat than places near the poles. Places near the equator are therefore hot, while places near the poles are cold. Thus, the air at the equator will rise due to convection, and this will create a belt of low pressure at the equator. Meanwhile, at the pole, the opposite will happen. The cold air will sink, resulting in a high atmospheric pressure belt at the poles. So, since air is high at the poles and low at the equator, we would expect that the wind would blow directly from the poles to the equator. However, this is not the case as the situation is more complex than this. Between these two pressure belts, there are actually some other pressure belts. Let us examine how these other pressure belts are formed. Remember that air rises at the equator due to high temperatures there. This results in a low pressure belt called the equatorial low or the doldrums. After the air rises to the tropopause, it is unable to rise further and therefore will diverge with one branch flowing towards the North Pole and the other towards the South Pole. The air which diverges above the equator doesn't reach to the poles, however, as it will sink down at 30 degrees latitude. As it sinks at 30 degrees latitude, that is north and south of the equator, it will form a high pressure belt called the subtropical high pressure belt or the horse latitude. When the air sinks to the surface at the subtropical high pressure belt, it will diverge with one branch moving towards the equator and the other branch moving polewards. Notice that the branch in the northern hemisphere, which moves to the equator, will converge with the branch moving from the southern hemisphere. This convergence also contributes to the air rising, which forms the equatorial low. Meanwhile, at the north and south poles, where the air is cold and dense, the air will sink to create a belt of high pressure. Again, the air which sinks to the surface will diverge, with one branch moving away from the earth and the other branch moving towards the equator. The branch which moves from the poles in the direction of the equator will not reach to the equator, however. This is because on its way it will converge with the air blowing from the subtropical high pressure belt. This convergence will result in air rising at about 60 degrees latitudes north and south of the equator, creating another pressure belt. This pressure belt at 60 degrees is called the subpolar low. After rising to the upper atmosphere from 60 degrees latitude, the air will diverge at the tropopause because it is unable to rise further. One branch will head towards the poles and the other towards the equator. In the upper atmosphere, above 30 degrees, this air converges with the air flow coming from the equator and sinks down to contribute to the formation of the subtropical high pressure belt. The other branch will, of course, sink at the poles. So I want you to notice some patterns. For example, each time air converges at the surface, notice that it also diverges in the upper atmosphere. Similarly, when it diverges at the surface, it converges in the upper atmosphere. Another pattern I want you to observe is that there are alternating belts of high and low pressure along the surface. So at 90 degrees, we have a high pressure belt. At 60, there is a low pressure belt. At 30, there is a high pressure belt again. And at the equator, there is a low pressure belt. And this occurs on both hemispheres. Finally, notice that there are three cells of air circulation on each hemisphere. All right, so we're going to talk a little more about these cells. But for now, let's look at the pressure belts once more. This time, uh, let's look at them on the globe itself. Since each area of high pressure is adjacent to an area of low pressure, a number of pressure gradients have been created. And remember, we said that pressure gradient is the initial force that causes winds. So these pressure gradients are responsible for initiating large scale winds that we refer to as planetary winds. If the Earth was not rotating, the winds would blow directly from the belts of high pressure to the belts of low pressure. However, we know that this is not the case. Because the Earth is rotating, another force acts on the winds besides the initial pressure gradient force. This is the Coriolis force. Remember, we said that the Coriolis force causes large scale winds to be deflected to the right in the northern hemisphere and to the left in the southern hemisphere. So the black arrows that we are seeing is showing, they are showing the winds as they would blow if the earth was not rotating. The white arrows, on the other hand, show the way the winds blow as a result of being influenced by the Coriolis force and therefore uh, as a result of being deflected to the right in the northern hemisphere and being deflected to the left in the southern hemisphere. Winds which blow from the poles to the subpolar low are called polar easterlies. Notice that they are blowing from either the northeast or from the southeast, and winds are generally named based on the direction from which they are blowing. The winds which blow from the subtropical high pressure belt to the subpolar low are called westerlies. So, once more, notice that the winds that are called westerlies, they are either blowing from the northwest or from the southwest. This third set of winds blow from the subtropical high pressure belt towards the equator. These are called trade winds. We can talk about the northeast trade winds and the southeast trade winds. The northeast trade winds are the prevailing winds over the Caribbean region. So, all of what we have discussed so far is to help us to understand the tricellular model. The tricellular model is a two-dimensional model which shows how energy is transferred polewards via three cells of air circulation. These cells are the Hadley cell, the feral cell, and the polar cell. The Hadley cell, as we can see, is the largest loop and features air rising near the equator, flowing poleward in the upper atmosphere, then descending at the subtropics before returning equatorwards near the surface. The cell in the middle is the feral cell. In this cell, air rises due to convergence at about 60 degrees, which is the subpolar low, flow equatorwards in the upper atmosphere, sinks again at the subtropical high pressure belt before returning to the subpolar low at the surface. The smallest and weakest cell is the polar cell, which involves air rising at the subpolar low, flowing polewards in the upper atmosphere, sinking at the pole before returning to the subpolar low at the surface. The model also shows two belts of instability due to air rising. At the equator, the trade winds converge to form the ITCZ. This ITCZ influences places with equatorial climates, bringing them heavy rainfall. At the subpolar low, warm air from the subtropics meet with cold air from the poles, and this forms a front. This front is responsible for uh, the development of mid latitude depressions in this location. So, the tricellular model has applications as well as limitations. In terms of its applications, it provides a starting point for understanding atmospheric circulation. It gives a clearer indication on the reasons behind the variation of climates between the equator and the poles. It also allows for some level of prediction of the weather. In terms of its limitations, it only indicates north to south movement of energy and fails to show that there are other major transfers of energy. For example, it does not take into account the middle latitudes east west air movement, such as the jet streams and the Rossby waves that disrupt the feral cell. It also fails to show how relief barriers, such as the Himalayas, may disrupt the movement of jet streams and surface level winds within the Hadley cell. Okay, so this is where I will stop. I encourage you to find some past paper questions on the topic and practice them. Thanks again for watching, and remember to like, to share, and to subscribe.